Welcome back to the Deep Dive. We are the place that takes your most complex source material, your articles, your white papers, your scenario-based questions, and delivers the essential knowledge shortcut, ensuring you walk away truly well-informed.
Today, we are moving past the AI and machine learning basics. If you're listening to this, you've probably internalized the concepts of, training data and algorithms.
Right.
Now, we stand firmly in what I'd call intermediate territory. The focus shifts entirely from what a model is to how it actually operates in the real world.
Exactly. And our source material for this is, it's just brilliant because it forces us to make these architectural and operational choices. This isn't a vocabulary test anymore.
No, not at all.
It's a deep dive into the engineering dilemmas. You've got efficiency trade-offs, deployment headaches at a massive scale, and what is probably the absolute cornerstone of modern AI compliance and governance.
This deep dive is purely focused on answering the questions that define production readiness. We're going to be unpacking the spectrum of model creation, analyzing the specialized hardware that, powers deep learning.
And the scalability, right? The kind you need for millions of users globally.
That's a big one. And integrating the critical tools required to ensure models remain trustworthy and, importantly, auditable over time. Our mission is to really solidify these concepts, giving you the practical why behind every tool selection.
Okay, let's unpack this. Let's start right at the beginning of the ML lifecycle, creation. When you start building a model, you face this core dilemma. Do you want speed or do you want maximum control? And this really splits the world into two camps. You've got the automated fast lane and then the detailed custom workshop.
That's a perfect way to put it.
So let's start with a classic, well-defined scenario from the sources. Say you're building an application, and it needs to recognize famous paintings from images that people upload.
A classic image classification task.
Exactly. It's been done millions of times. So if speed, accessibility, and just minimal engineering time are your non-negotiable priorities, where do you even begin?
You start with a tool like Cloud Vision, or more generically, AutoML. The core definition we work with for AutoML is, it's beautifully simple. Data in, model out, no code.
No code.
No code. It is the ultimate expression of abstraction in the entire ML lifecycle.
That concept is easy to grasp, but for you, the listener, who is now moving into this intermediate understanding, we need to know, how does this no-code magic actually happen, and what exactly are you giving up to get that speed?
Well, what you're giving up is the ability to fine-tune the internal machine learning engine. In a traditional custom training job, the ML engineer would have to make hundreds of critical decisions.
Like what? What kind of decisions are we talking about?
Oh, all sorts. Do we use a ResNet architecture? Should I try one of these new transformer models? What's the optimal batch size for my data? What is the ideal learning rate? And, how should I schedule its decay over the training epochs?
So it's a huge number of variables.
A huge number. And AutoML entirely abstracts this complexity away.
So it's not that the complexity just vanishes into thin air.
Yeah.
It's that the system is handling it for you. It's kind of like an automated search engine for the best possible model structure.
Precisely. AutoML uses techniques like neural architecture search, they call it NAS, and hyperparameter optimization, to try out literally thousands of combinations of algorithms and configurations on your specific data set. It tests them, it scores them, and then it just presents you with the best performing model. You never see the underlying code or the choice of algorithm.
So the value proposition here is enormous speed to market and massive accessibility. I'm thinking of a team that specializes in, say, web development, but they need a highly competent image classifier for their app.
Right.
They don't need to go out and hire a team of ML PhDs. They just provide the labeled data, and in return, they get a deployable model.
That's the primary differentiator. AutoML is just unbeatable for efficiency in these standardized tasks. Think image classification, video intelligence, or standard tabular data classification. If the problem fits neatly into a common ML category.
Use AutoML.
Yes, it allows your specialized developers to focus their resources on the application layer, building the user interface, managing payments, integrating APIs, rather than reinventing the wheel on the modeling side.
But there's a trade-off.
There's always a trade-off. And here, it's that you surrender control. If you need a cutting-edge proprietary loss function or some bespoke architectural tweak for your specific problem, AutoML will simply not allow it. It can't.
And that lack of control is the perfect segue. It's the exact reason why we moved to the custom workshop. If the problem is novel, let's say you're interpreting highly complex proprietary sensor data in some non-standard way.
Right, something brand new.
AutoML is useless. We have to write the model ourselves, often using frameworks like TensorFlow or PyTorch.
Yeah.
So if we've written our custom Python code, why do our sources immediately point us toward Vertex AI Training? Why not just, run the code on a big cloud server?
The decision to move to Vertex AI Training is a really important one. It's a transition from running code on infrastructure to running code on a managed service. You can absolutely just spin up a massive server or compute engine deep learning VM and run your code there, but
Okay.
but that choice imposes maximum operational responsibility on you.
Okay, tell us about that responsibility. What are the headaches that running on a standard virtual machine, a VM, forces upon the ML engineer?
Oh, think about just the prerequisites for training a large model. First, you need to select the correct operating system image. Then you have to install all the necessary libraries, TensorFlow, CUDA drivers, specific Python dependencies, and you have to ensure they are all compatible with each other.
Which can be a nightmare.
It can be a total nightmare. Then you have to manage patching the OS for security vulnerabilities, and crucially, you have to handle the scaling. If your model requires, say, 20 GTUs to train in a reasonable amount of time, you have to manually provision and coordinate all 20 of those machines, manage the network connection between them, and ensure there's fault tolerance if one of them fails mid-training.
And the scenario in our source material specifically stated that the user wants to train a custom model, but, and this is the key phrase, does not want to provision and manage training servers manually.
Exactly. Vertex AI Training eliminates this entire infrastructural burden. It is a managed service where you submit your containerized custom training code as a job. That's it.
So you package your code up in a container, you give it to Vertex, you say, run this.
That's the essence of it. Vertex then handles the entire orchestration. It provisions the necessary compute cluster. It distributes your code efficiently across multiple nodes if you need them. It manages the scaling, monitors the job's progress, and then, this is important, it spins down the entire cluster when the job completes so you start paying for it.
And the critical benefit here is that it auto-scales the infrastructure. The developer gets to focus purely on the modeling code, not on being a cluster management expert.
Yes, that's the whole point.
So the core trade-off here is maximum flexibility with minimum operational overhead. The raw compute engine VM gives you 100% control over everything, but Vertex AI Training gives you, maybe 90% control over the code while handing off 100% of the operational and infrastructural management to the cloud provider.
That's a good way to look at it.
That's a huge productivity gain, especially when you're dealing with these massive distributed training jobs that might take hours or even days to run.
And that efficiency is so crucial because once a model is trained and deployed, the work cycle is far from over. It's really just beginning.
And that brings us to the model improvement cycle. This is so important. We have a scenario about an e-commerce site, and they're using a recommendation model. They want to improve the quality of those recommendations over time.
A very common goal.
The source insight provides the solution, and it feels like the secret sauce for production AI. It says, save a history of recommendations and results of the recommendations in BigQuery to be used as new training data.
This is one of the most foundational principles for successful MLOps or machine learning operations. Models are not static pieces of software. They're dynamic algorithms that learn from the world.
Can you give us an example of that?
Sure. If your e-commerce model recommends a running shoe, let's call that recommendation A, but the user ultimately clicks on and buys a hiking boot result B, that A to B pair is a new, incredibly valuable labeled data point.
It's real-world feedback.
It's the best kind of feedback.
And we have to log the history of the initial prediction and the result. But why BigQuery specifically, and why is this continuous loop so vital for the model's health?
BigQuery is the ideal repository for this because it is a highly scalable, petabyte-scale data warehouse that's optimized for analytic querying. When you start collecting a massive stream of prediction feedback, millions of these A to B pairs every single day, you are talking about petabytes of historical data very quickly.
And most databases would just fall over.
They would, but BigQuery can handle this ingestion, and more importantly, it can serve as the data source for the next retraining job without breaking a sweat. It's built for that scale.
So let's play this out. If the model is not fed this fresh data, what happens to it over time?
It suffers from decay or drift. User preferences change, new products are introduced on the site, competitors shift their pricing strategies, macroeconomic trends evolve. All these things affect user behavior.
The world changes.
The world changes. So if you only train the model on 2023 data and then just let it run in 2025, its performance will degrade because its understanding of the world is hopelessly outdated.
So by constantly feeding back the real-world results, the purchases, the clicks, the rejections, all of it, you keep the model perpetually up to date. It reflects current user behavior.
That's it. This historic feedback loop is absolutely non-negotiable for any system that's aiming for continuous organic improvement. It's what separates a toy project from a real production-grade AI system.
That really closes the loop on creation and iterative refinement. So once the model is refined, the next huge operational hurdle is getting it in front of millions of global users and doing that securely and efficiently. This takes us into the world of deployment architecture.
A whole different set of challenges.
Here is a classic dilemma from the sources. We have a new application for globally distributed users to upload pictures. It must support millions of concurrent users, and the developers have a single, very strict mandate. Focus only on building code.
Ah, the dream mandate.
No infrastructure management, please.
The millions of concurrent users, combined with focus only on building code, is the ultimate architectural constraint. It's a huge tell. It immediately rules out any solution that requires manual capacity planning or any kind of server maintenance.
So the answer is
The correct solution here is App Engine.
App Engine, the ultimate abstraction layer, right?
Yeah.
It's a platform as a service, a PaaS. Can you explain in detail why App Engine stands so far apart from its alternatives, like GKE or Compute Engine, in this specific scenario?
Yeah, of course. App Engine is a fully managed environment. When the developer deploys their application code, the platform itself takes on the responsibility for the entire runtime environment.
What does that include? What does entire environment mean?
It includes provisioning the virtual machines, managing the operating system, applying security patches, handling all the networking, and providing built-in load balancing. All of it.
And the scaling. That's the crucial point here for supporting millions of concurrent users.
App Engine's auto-scaling is, it's seamless and it's instantaneous. If traffic spikes from 5 users to 5 million in an hour, like after a Super Bowl ad or something, the platform's mechanisms automatically spin up new instances, distribute the load, and ensure high availability.
And the developers do nothing.
The developers don't have to write a single line of scaling configuration or even look at a utilization dashboard. They might not even know it happened until they check their build. That's the key operational difference.
Okay, now let's introduce the challenge, as an intermediate listener might ask. If App Engine is so easy and so scalable, why would anyone ever choose Google, Kubernetes Engine GKE, or Raw Compute Engine for a high-traffic ML application deployment? What are the trade-offs we're avoiding with App Engine?
The trade-off is control, which, at the absolute fringes of scale, often translates to cost and complexity. GKE, while incredibly powerful for container orchestration, requires you to manage the cluster itself.
So you're back to managing things.
You're back to managing things. You have to decide on node pools, set autoscaler parameters, monitor the health of the control plane, manage complex networking layers like service meshes. This requires specialized SRE or DevOps knowledge, which completely violates that focus only on code rule.
So the developer using GKE still has a pretty significant operational responsibility. And what about just Raw Compute Engine?
Compute Engine is simply infrastructure as a service. You're just renting raw VMs. It offers maximum control over the operating system and the hardware configuration, but it gives you zero management help.
You're on your own.
Completely. To handle millions of concurrent users on CE, you would have to manually implement and manage complex global load balancing, write your own custom scaling scripts, and manage the health checks and redundancy across dozens of regions. The management burden and the operational cost just increase exponentially.
Which is the exact friction the developers in our scenario wanted to eliminate.
Precisely. So App Engine gives up that fine-grained control for total, hands-off operational convenience and massive built-in scale.
Okay, shifting gears a bit to security. We've deployed our famous paintings application, but now we need to test it. We have a limited group of external partners, and we need to give them access for just 24 hours.
A classic beta test scenario.
The constraints are tight. Secure, temporary access to the cloud storage bucket for uploads, but, and here's the kicker, not all users have a Google account.
And that last part is the key constraint. It's a classic example of needing granular, time-bound access without imposing a huge identity and access management, or IAM, burden on the external user. We can't use standard App Engine authentication because that requires Google accounts.
So the technical solution, which is a really elegant intermediate concept, is the signed URL that expires after 24 hours. How does a cryptographic signature in that URL make this secure, temporary, and account agnostic all at once?
The signed URL isn't a username and password. You should think of it more like a policy document that's been baked right into the URL string itself. So when your authorized service account generates this link, it uses its private key to generate a cryptographic signature. This signature proves the link's legitimacy. And embedded right in that URL are three crucial parameters. The ID of the resource, like the bucket path.
So it knows what you can access.
Right. Then the permission being granted, for example, storage.objects.create, which means you can upload something.
It knows what you can do.
Exactly. And finally, the fixed expiration timestamp. In this case, 24 hours from now.
So when the external user, who has no Google account, uses this link to upload an image, cloud storage verifies the signature, sees it was generated by an authorized entity, and then it just checks the clock. If the signature is intact and the time hasn't passed, the request is permitted, even if the user is completely anonymous to the cloud environment.
Exactly. The URL is the temporary credential. It's self-contained. And once that embedded expiration time is reached, the Cloud Storage API will reject any request using that link, treating it just like any other standard unauthorized access attempt. It provides a highly auditable, secure, and crucially self-expiring mechanism.
So why is this method superior to the alternatives? I mean, why not just try to password protect the bucket or set up a temporary IAM role for these testers?
Well, attempting to password protect a cloud storage bucket is simply not a native time-limited security feature of the service. It would be clunky, less secure, and complex to manage. And setting up temporary IAM roles or service accounts is powerful, but it's often overkill for this kind of use case. And more importantly, it usually requires the external user to have some form of Google identity, which the scenario explicitly rules out. The signed URL offers the absolute lowest friction for the external user while providing the highest security guarantee of automatic expiration. It's the right tool for the job.
Perfect. We've covered the software and the scalable deployment strategy. Now let's enter the engine room, the hardware. The choice of accelerator fundamentally impacts how quickly we can iterate on our models and how much we end up spending.
A huge factor. The hardware choice can make or break a project.
And the sources outline a roadmap decision. A company is moving its model training from cloud GPUs to cloud TPUs, which offer better results. This implies that the versatile GPU, which we all know and love, is no longer the optimal choice for them.
Right.
To understand this switch, we need to really detail the specialization of each of these pieces of hardware.
It's a classic decision point in deep learning architecture. GPUs are fantastic, but they are generalists, really. They're optimized for versatility. TPUs, on the other hand, are hyper-specialized. They are optimized purely for deep learning at scale.
Let's start with GPUs. We know them as graphics processing units. Their original design was for all the highly parallel tasks you see in gaming and video rendering.
Right. Their architecture involves thousands of small, simultaneous processing cores. This design turned out to be brilliant for the parallel arithmetic needed in deep learning, specifically dense matrix multiplications.
So they were sort of a happy accident for AI.
A very happy accident. They became the de facto standard because they were already available in the market and were extremely flexible. They support every framework, every model type, from classic machine learning all the way to complex deep learning. They're the workhorse.
So if the GPU is the powerful, versatile workhorse, what did Google do differently when they created the Tensor Processing Unit, or TPU?
They optimized the hardware specifically for the data structure that defines deep learning, the tensor.
Which is just a fancy name for a multidimensional array.
Exactly. And deep learning training is, at its core, just performing massive repeated matrix multiplications on these tensors. So Google designed the TPU to do only that, but to do it much, much faster and more efficiently than anything else.
How is the TPU architecturally different from a GPU? This is where the intermediate detail is so crucial for our listeners.
The key is an architecture called a systolic array. This is the secret sauce. Unlike a GPU, which routes data through standard pipelines and memory, the systolic array in a TPU is a big 2D grid of dedicated matrix multipliers that are all tightly coupled together.
Okay, what does that mean in practice? How does that change things?
It means data flows across this array in a highly controlled, synchronized stream, almost like a wave. This design drastically reduces the need to constantly load and unload the model's weights and activations from external memory, which is a major, major bottleneck for GPUs.
So it's all about reducing that latency, that back and forth to memory. By eliminating that and focusing solely on this one operation matrix multiplication, TPUs achieve a massive performance increase.
A massive increase, specifically when you're dealing with the huge tensor sizes that are characteristic of, say, large language models or deep neural networks for image processing.
Funny.
They also often use reduced precision arithmetic, like something called bfloat16 instead of the standard FP32. Now, while this sacrifices a tiny, tiny bit of numerical accuracy, which is often totally irrelevant in deep learning, it effectively doubles the throughput of the calculations.
So the rationale for switching then is pure optimization. When you're training a model that takes a week on the latest GPU cluster, switching to TPUs might cut that time in half. Or it might allow you to use larger batch sizes, which can lead to better results because you can iterate faster or use more compute-intensive complex models that were previously just prohibitively expensive or slow to train.
That's the whole game. The trade-off, of course, is that TPUs are highly optimized for TensorFlow, which makes them a bit less versatile for some other niche frameworks out there.
Got it. The engine is in place, the model is trained. Now, we shift entirely to the operational phase, ensuring trust, compliance, and longevity in a dynamic production environment. And this is often the hardest part of the entire process.
Oh, definitely. Training is a one-time hurdle. Governance is a permanent commitment.
So let's revisit that analogy we used earlier of the student trained in 2020 and deployed in 2025. That discrepancy, where the production data no longer matches the training data that's drift,
Mm-hmm.
and if it's left unchecked, it's a silent killer. It slowly turns a highly accurate model into a liability. So how do we catch this change in this statistical environment?
The necessary tool for this is Vertex AI Model Monitoring, and the specific indicator we are watching for is the prediction drift metric. This isn't just about watching the model's accuracy degrade over time. It's about proactively detecting the cause of that degradation before it becomes a major problem.
Okay, so what exactly is the monitoring tool comparing to establish that drift is actually occurring?
It's quite clever. It creates a baseline statistical profile of all the features that were present in the original training data. For example, the average age of users, the distribution of income levels, or the range of credit scores in that training set.
So it takes a snapshot of what normal data looked like when the model was trained.
Exactly. Once the model is in production, the monitoring system constantly compares the statistical distribution of the incoming live prediction requests to that static training baseline.
So if a model was trained mostly on data from, say, a US-based user base, and then the company starts expanding heavily into Europe, where customer demographics are statistically quite different.
The monitoring system will flag that distributional shift immediately.
That makes perfect sense.
If the statistical distance between the live data and the baseline exceeds a predetermined threshold, which is often calculated using methods like the Jensen-Shannon divergence, the system generates an alert. And this immediately tells the MLOps team, stop. The world has changed. Your model is consuming data it was never trained to handle effectively.
That is so crucial. Unlike a traditional software team where a bug causes an immediate, obvious crash, an ML team has to deal with performance degradation that occurs subtly over weeks or even months.
Yes, it's a slow burn.
So monitoring transforms that passive decay into an active, actionable alert. And that allows them to cycle back, use that feedback data we stored in BigQuery, and retrain the model before its accuracy drops below acceptable business thresholds. It's the essential operational component for reliability in any real production system.
Absolutely. It's your early warning system.
Now we have to address the compliance crisis. This is a big one. We have a loan approval model that's been deployed on Vertex AI. It rejects an application. Now, compliance regulations, like those governing fairness and non-discrimination in lending demand, that we provide the specific features that contributed most to that prediction.
We have to open the black box.
We must move from a black box to a completely transparent system.
This is the moment where technology intersects directly with ethics and regulation. And the solution is Vertex Explainable AI, specifically utilizing its feature attributions capabilities.
Explainable AI is a pretty broad term. What are feature attributions, and how do they move us beyond just generic high-level explanations?
Feature attributions provide a localized quantitative analysis for every single prediction the model makes. So instead of giving a general rule like income is important in this model,
Which is not very helpful to the person who was rejected.
they're not helpful at all. Instead, it provides a specific weight for every input feature on that single rejected loan application. It asks, How much did the applicant's income specifically push the prediction toward approval, and how much did their debt-to-income ratio specifically push it toward rejection?
Wow, so this sounds incredibly detailed. It's like it assigns a positive or a negative score to each input feature, reflecting its influence on the final outcome for that one person.
That's the key mechanism. It utilizes advanced techniques like SHAP, which stands for Shapley Additive Explanations, or integrated gradients to calculate these attribution scores. And the math requires that the scores must sum up to the final model prediction.
What does that mean for the person who was rejected?
It means you can legally and ethically provide them with a clear, data-driven rationale, you can say. Your application was rejected because your current debt-to-income ratio negatively contributed 55% to the decision, and your insufficient credit history contributed another 20%.
The power of this is that it transforms the model from what feels like an arbitrary decision maker into a fully auditable component of a business process.
Exactly.
It satisfies the regulatory requirement of due process and non-discrimination by allowing us to confirm that the rejection wasn't based on a prohibited feature like race or gender, but on legitimate financial metrics like debt and credit history.
Absolutely. And this capability is not optional in regulated industries like finance, insurance, and healthcare. If your system cannot generate feature attributions, it often cannot be legally deployed regardless of how accurate it is. It is the technical bridge between a successful ML model and a compliant, trusted business asset.
That sets the stage perfectly for governance. Finally, let's wrap up our toolkit by looking at some specialized integration tools and then the highest level of regulatory enforcement. Data residency.
The really tough stuff.
Let's start with BigQuery ML, or BQML. It appears repeatedly in the sources as an alternative approach to model building. It allows ML to be embedded directly into the data warehouse workflow. Can you explain BQML's function and why it is so revolutionary for non-ML engineers?
BigQuery ML is a complete game changer because it allows analysts and BI professionals to create, train, and deploy sophisticated machine learning models using nothing but standard SQL queries.
Using just SQL.
Just SQL. The data never has to leave the BigQuery environment.
Let's delve into the friction that BQML eliminates. We mentioned that ETL, or extract, transform, load, friction earlier. For an intermediate audience, what does an analyst currently have to do that BQML eliminates entirely?
A traditional workflow is, frankly, a nightmare of serialization and environment management. An analyst has, say, 10 terabytes of clean, structured data sitting in BigQuery.
The dream scenario.
The dream. But to train a model on it, they must first extract that data, often sampling it down to save time. Then they have to transform it into a format that a Python environment can use, like a pandas data frame. And then they have to load it onto a completely separate compute environment, a VM or a Vertex AI job.
They have to manage that whole pipeline?
They have to manage the compute environment, the Python libraries, the serialization and deserialization logic. It's complex and error-prone.
BQML skips all that.
It collapses all those steps into a single create model SQL statement. The data never moves. The compute happens within the BigQuery ecosystem.
That's incredible.
It dramatically accelerates time to insight, and crucially, it democratizes advanced modeling. An analyst who speaks fluent SQL doesn't need to learn Python or specialized ML frameworks or infrastructure management to run a linear regression or a logistic model for classification or even complex matrix factorization for recommendation systems.
So the key benefit is speed, accessibility, and the elimination of these complex, brittle data transfer pipelines. It allows predictive capabilities to flow directly from the data warehouse, which is where the business intelligence team already lives and works.
And this capability is constantly expanding. BQML now supports models like boosted trees and certain deep neural networks. It just removes the barrier to entry, turning massive datasets into predictive engines almost instantly without that costly, complex handoff between the data team and the dedicated ML engineering team.
Okay, let's tackle the highest stakes scenario in our sources. Data residency. We have a healthcare provider in the Middle East. They need to summarize confidential patient notes using a powerful tool like Gemini on Vertex AI. The regulatory requirement is absolute. The data must never leave the region. This demands technical safeguards that are, for all intents and purposes, unbreakable.
This is a perfect test of architectural maturity. Relying on a simple contractual clause or some header in the API request is completely insufficient. The configuration requires a two-pronged technical enforcement strategy.
Okay, and the required configuration is use the specific regional API endpoint, for example, me-central1-aiplatform.googleapis.com, and a diverse policy control using a VPC Service Control perimeter. Let's look at the regional endpoint first. Why is that step one?
Using the specific regional API endpoint is the first required step. It ensures that the request, which contains the confidential patient notes, is directed to and processed entirely by the infrastructure that is physically located within the mandated geopolitical boundary. In this case, the Middle East, me Central 1.
So the API call itself never traverses networks outside that define geography for processing.
Correct. This satisfies the baseline residency requirement.
That the VPC Service Control perimeter is the true failsafe. Why is that second layer so absolutely essential in a high compliance scenario like this?
VPC Service Control, or VPC SC, creates a virtual policy boundary. You can think of it as an impenetrable security fence around your project's cloud resources, including your BigQuery data, your cloud storage buckets, and your Vertex AI services. It acts as an enforcement layer that actively intercepts and denies any API calls that attempt to violate that boundary.
So this perimeter can actually override even a user's permissions if they try to do something non-compliant.
Exactly. If a well-meaning but hasty developer tries to send the patient notes to a global API endpoint, or tries to copy the data to a cloud storage bucket in an external project that's outside the perimeter, VPC SC intercepts that API call and denies it outright.
It's a hard stop.
It's a hard stop.
Yeah.
The perimeter prevents data exfiltration, whether it's accidental, like a misconfiguration, or malicious, like an insider threat.
So in highly regulated industries, the policy is not just to rely on dedicated regional infrastructure, but to combine it with VPC service control. This provides the technical, enforced guarantee that the confidential data remains absolutely confined to the mandatory region, satisfying that must never leave the region mandate.
It moves security from a recommendation or a best practice to a technological requirement that's enforced at the API level. It is, without a doubt, the gold standard for compliance architecture.
That brings us to the end of our deep dive into the intermediate AI and ML toolkit. We didn't just define terms today, we really dissected the necessary architectural trade-offs that you have to make.
Yeah, we saw the full spectrum of model creation. We realized that the choice between the speed of AutoML and the control of Vertex AI training is purely dependent on the novelty of the problem and, the operational budget for infrastructure management.
Right.
And we also established that critical mechanism for continuous improvement, the BigQuery feedback loop that constantly fights model decay.
And we clarified that massive scale global deployment often requires the zero management convenience of App Engine, contrasting its ease with the control and complexity of CKE. Meanwhile, temporary secure external access is solved not with clumsy passwords, but with cryptographically sound signed URLs.
The engine room discussion detailed the crucial difference between the versatile GPU and the hyper-specialized TPU, a choice driven by the massive scale and architectural demands of modern deep learning. And finally, we covered production governance, model monitoring to prevent the silent decay of prediction drift, and Vertex Explainable AI specifically feature attributions to ensure auditability and compliance in high-stakes decision-making scenarios.
It is so evident that the intermediate AML toolkit demands a skill set that combines coding expertise with strategic architectural decision-making, governance awareness, and a deep, deep appreciation for the why behind every single tool selection.
Which leads us perfectly to our final provocative thought for you to consider. We spent a significant amount of time discussing feature attributions, the technological solution for explaining why a model made a past decision, thereby meeting compliance. However, merely explaining a rejection is reactive. The next frontier in AI governance is proactive, designing models to be fair from the outset, rather than just explaining unfair outcomes after the fact.
That challenge, moving beyond just explaining past biases to actively engineering for equitable outcomes, that requires integrating these monitoring and explainability tools, not just as compliance checks at the end of the pipeline,
Right.
but as continuous feedback mechanisms that influence the model structure and training data from day one. It transforms the engineering problem into a deeply ethical and design challenge.
Indeed. The technology gives us the ability to look inside the black box. The question now is, how do we use that vision to build a more responsible system?
Thank you for guiding us through this essential intermediate toolkit.
Always a pleasure.
And thank you for joining us on this deep dive. We'll see you next time.